I'm Greg Gilbert. I'm a postdoc at UCLA, and I'm going to be telling you about exactly what it says on the tin here. All right, so let's start by just motivating things with our own solar system. There are some basic observations that we can make. The first is that the planets come in three sizes: the terrestrials, the gas giants, and the ice giants. And then we can also see that all of the orbits in our solar system have very low eccentricities. And at the same time, they also have quite low inclinations. And the natural interpretation of this is that the planets all formed in a disk at the same time that the sun was forming. And this has been known about for, a couple hundred years now, so you would think that we understand it pretty well, but there's still a lot of details that we're working out. And so just to orient you to just the broad picture of how planets form, it happens over, many orders of magnitude in time, many orders of magnitude in scale. Everyone in this room knows this picture. You collapse from a molecular cloud into a disk, it starts forming. The cores that are able to accrete to about 10 times the mass of the Earth in terms of rocky materials, those can undergo runaway accretion with hydrogen helium gas. You form your giant planets. After the gas disk dissipates, continue to form terrestrial planets through oligarchic growth. And then over these long time scales of up to billions of years, you have dynamical gravitational interactions between the planets that can lead to migration, can excite eccentricities, can excite inclinations. And it's this last portion that I'm really focusing on by measuring the eccentricities of the planets. And so, the reason we want to measure the eccentricities very precisely is these different processes has different effects on what the modern day eccentricities look like, right? So scattering will excite eccentricities, disk migration, if the planets form while the disk still exists, that will damp down eccentricities, and then giant impacts are a little more complicated because you need some eccentricities to get the impacts in the first place, but once they happen, that tends to damp down eccentricities as well. All right, and if we want to do a population-level study of eccentricities, we really need to look at the transiting planets, because that's the only way that we're going to get enough planets to say something significant about the population. We've got thousands of planets from transits, primarily from the Kepler mission, but only dozens or hundreds from these other methods. And there's advantages to the other methods, either from direct imaging or Doppler, but transits are really going to be the way to go. And so just to give you a little bit of a state of the field, as of about a year ago, there's this great work by Brendan Bowler and collaborators showing that there's a difference in the morphology of the eccentricity distributions between giant planets versus brown dwarfs. David Kipping, about a decade ago, showed that Doppler-detected planets are pretty well described by a beta distribution with a mean eccentricity of about 0.3. And then Vincent Van Allen showed that there was this very, very significant difference between the singles and the multis of transiting planets, where the multis had much lower eccentricities. Okay, so we've had the data from the Kepler mission for a decade now. Why has an eccentricity study of this scale not been done before? And the answer is just that measuring eccentricities is very hard because it's an under-constrained problem. For most Kepler quality transit light curves, we don't have enough information to resolve the transit impact parameter with a high degree of precision, which means we've really only got the one observable, which is the transit duration, the time from first to fourth contact during the transit. But the transit duration is both affected by the speed during the orbit, and that's what probes eccentricity, and that's a two-parameter problem, both the orientation of the orbit and the eccentricity itself. And then it's also sensitive to the transit impact parameter, which changes the chord length, right? So you've got duration, you've got the chord length, and that's the transit impact parameter, how far off from the center, and you've got the orbital velocity sensitive to the eccentricity. And here's where the know thy star part comes in, is if we want to make a measurement of the eccentricity, we need to compare to the expected transit duration for a circular center crossing orbit. Do a little bit of mathematical rearranging, and it turns out you can express that purely in terms of the stellar density, which now, thanks to Gaia, we have very precisely for essentially the full Kepler population. Okay, And so working with UCLA PhD student Mason McDougall, we worked out this great way to, without refitting any light curves, do a whole bunch of mathematical jujitsu, and we get the eccentricity measurements as if we had fit eccentric models. There's a lot of reasons you don't want to go through the hassle of fitting eccentric models directly. I'm not going to get into them. It's just very time-consuming. So we had this great method for getting eccentricities without any light curves. These, by the way, are the working definitions of planet size classes I'll be using for the remainder of the talk. And so we use this important sampling method to turn the Gaia data plus the Kepler data into measurements of eccentricity, and we got referee number 2. And I want to be very clear, this is how peer review is supposed to work. The referee raised some very valid criticisms, some concerns about how the Kepler team had fit the light curves. The Kepler team did a great job of getting all of the uncertainties on radius and duration down to about the 10% level, but now we're trying to push things down to the couple of percent level. So there was a lot of work that would need to be done in order to get the reliable measurements we needed to make eccentricity results. And so the referee said, I'm not going to believe your results until you reprocess all of the Kepler light curves. So that's what we did. We refit the light curve from about half of the Kepler sample, addressing all sorts of issues. I'd be happy to talk about the details of the pipeline with anyone afterwards. And so I call this pipeline Alderon. And I want to highlight the work that UCLA undergrad student Paige Entrekin did. She did a phenomenal amount of work putting together this visualization software so that we could quickly verify that all of the fits were working. We fit everything multiple times as we were developing things, so just looking at thousands and thousands of light curves. Okay, so we're back to where we were a few moments ago, where we're analyzing 1,600 Kepler planets, except now, instead of using the DR25 posterior chains, we're using our own bespoke transit fits. Okay, so turn those into eccentricity posteriors. And one thing I want to highlight here is that the posteriors are non-Gaussian and highly asymmetric. So you can't just approximate them as a point with uncertainties. And so what you need to do is what we did, and we feed them into a hierarchical Bayesian model. One thing that I really like about the model that we used is it made very minimal assumptions. We really only assumed that the distribution had to be smooth. And so the way you do that is you essentially fit it as a histogram, use a Gaussian process to regularize it. Again, only assumption is that the distribution is smooth. And what we found is that the shape of the distribution is this quasi-exponential shape in orange. Looks pretty similar to the beta distribution that's popular in the literature. Also, the half-Gaussian distribution is a pretty good fit. Don't use the Rayleigh distribution. That's something that people have been using for a while now. There's some good statistical mechanics arguments behind it, but it turns out to not be a good description of the exoplanet eccentricity population. And so we also found that the distribution is self-similar for all of these planet size classes. And if you plot them next to each other, you can see there's this clear trend. We're going towards larger planets. There is a higher eccentricity. And we could stop here. This would be an interesting result. But we have 1,600 planets, so we slice it more finely, and we see that there's this very sharp transition right around 3.5 Earth radii, right around the size of Neptune. And the large planets are about 4 times the eccentricity of the small planets on average. And it's the same exact shape for singles and multis, with an enhancement factor of about 2.5. And these eccentricity measurements fit in really, really nicely with measurements that have been known about in the literature. We can put it very simply. We know that small planets are very common, and large planets are quite rare. We also know that these small planets can form around stars with basically any metallicity down to that metallicity cliff that Jesse talked about. And as a number of people have alluded to, said specifically, you need high metallicity in order to form giant planets. And now we see this eccentricity measurement fitting in with the same exact transition at the same exact location at 3.5 Earth radii. We've got low eccentricity small planets, high eccentricity large planets. And this tells us that really there are two channels for planet formation. There's the small planet channel, forming the super-Earths and the sub-Neptunes, and then there's the large planet channel forming the gas giants, the sub-Saturns and the Jovians. Okay, and we wanted to make sure that we were actually measuring a property of radius and not something covariant with period or metallicity, because the large and the small planets don't exactly have the same period or metallicity distributions. And so the main takeaway I want you all to have from these two plots is that, across all metallicities, across all periods, the eccentricities of the sub-Saturns and the Jovians are higher than that of the small planets. So yeah, there's some effect from period and metallicity here, but the dominant effect is radius. And then we also found that there's this really neat feature in the radius valley where if you slice, instead of in radius, you slice parallel to the radius valley here, we see this subtle bump up in the eccentricities of planets within the radius valley. And so the question is, what causes this? Possibly measurement error. We did a lot of work to rule out any sources of measurement error, extensive injection recovery tests. As best as we can tell, it's not any sort of measurement issue. So then we thought maybe it can be caused by mergers. You take two super-Earth cores, smash them together, you get an oversized core smack dab in the middle of the radius valley. You can do it that way, or you can do it from the top down by stripping off the atmosphere from a sub-Neptune. And I like the second way a little bit better because it requires less fine-tuning. You can take a Mars-sized body, smash it into a sub-Neptune, and basically strip off the whole envelope. And then, if anyone has ideas for other methods that could cause this, I'd be curious to hear them. And this radius gap measurement fits in really nicely with a bunch of other measurements that have been made over the past year, which show that these radius valley planets, they're more eccentric, they're further from resonance, and they also break the P's in the pod pattern. And so this suggests that these planets in the radius valley have probably experienced some level of dynamical disruption. And so I'll give you one text-heavy slide. We've got this picture of planet formation that's forming where the planets form maybe on circular orbits, and then to get eccentricities, they have to be excited by giant planets. So we'll look at this as properties of other stellar and system properties soon, and I will leave you with a couple of plots and be happy to take questions.
Looking for reviewer number 2. And the other hypothesis is those gap planets are actually binaries, if David's not paying any attention.
Hi, this was a really, really interesting talk. Thank you very much. I'm Fede from Birmingham. You sometimes showed all the plots about the eccentricity with the options for single planets and planets in multiplanetary systems. I was wondering, do you see trends in eccentricity within multiplanetary systems? Or do multiplanetary systems that have more eccentric planets, do they all tend to be more eccentric, or do they still follow this very specific radius relationship?
So you're asking about higher multiplicity of, say, 2 versus 3 planets or 4 planets? Or?
I wonder whether a multiplanetary system that has one eccentric planet is more likely to have all the other planets also have some kind of eccentricities, or whether the size of the planets following this plot is the main driver for this eccentricity trend.
Gotcha. That's something we're working on figuring out now. It's actually very difficult to make any strong claims about individual planets, right? We can say as a population, if we look at these 75 planets, they statistically have this property, but the individual planet constraints are very broad.
Okay, hi Greg. Did you say what it is exactly that excites the eccentricities of giant planets?
We're not.
According to your modeling, or
we're not really sure. Maybe the giant planets are more likely to form with higher eccentricities in the first place, but we're kind of just hand waving and speculating now. We don't really know. Yeah.
This is Dan Huber, Hawaii. So one advantage of refitting all the light curves, all the work that you've done, is that you've also presumably improved the RP over R star measurement from prior to what was done from the Kepler team. So my question is, do you see any interesting new features in just the radius distribution of planets, for example, the radius gap, the valley? Is it emptier than it was before, like we see for the astroseismic sample? And I promise I'm not reviewer number 2.
Yeah, not as... I want to stress again, the reviewer did exactly what the reviewer was supposed to do. So I poked fun, but they did a great job. We didn't see the radius valley clear out as much as we expected to. We really thought it might clear out a lot. We did see a decent number of individual targets that were like, oh, maybe that's a radius valley planet, and then we remeasure it. We're like, nope, that was some issue with the impact perimeter measurement. But yeah, we were kind of surprised that the radius valley didn't statistically seem to clean out all that much.
Okay, we're going to leave it there. Let's give Greg a hand.